We had previously discussed that if you have a weak acid and base, you can make a mixture, and then we were discussing what happens if you put just a pure weak acid into solution. And so we did examples with ammonium and with acetic acid. But we're going to introduce a new one because there's two parts to this I want to talk about. Let's talk about carbonic acid, H2CO3. This is capable of turning into H+ and bicarbonate, HCO3-. This acid is acting as an acid. It breaks apart, it gives away H+ and bicarbonate. And I will tell you the Ka of H2CO3 is 4.5 times 10 to the negative 7. So make that negative a little clear. Let's try a solution here. Let's say we start with 1 liter of 0.1 molar, we'll get a little more suffix, there we go, molar H2CO3. So we use this solution and we are going to find pH. And so, again, 1 liter, just so our molarity will also be our moles, makes our calculations a little easier. I can solve the initial amounts of this chemical. I can say I started with 0.10 mole of my acid. And before anything has had a chance to react, there's none of my other materials. This was just pure weak acid in water. Now, take a minute, try to use what we learned in video 3, and see if you can find the pH of this solution. So go ahead and pause here, and then come on back. Alright, if you gave it a shot, had a chance, let's walk through it. Well, there's going to be some change. So we have to think about what is happening here. If I have nothing but the weak acid in solution at the very start, well, it can fall apart and go to the right, make products. But at the very beginning, there's no products. They are unable to go to the left. So there is a rate going to the right, and there is absolutely nothing going to the left. As a result, at the very beginning, all I can do is lose starting material. So I'm going to lose some of my starting material. I'm going to gain some products. And so I had a few people ask about, when do you make one side minus X and which side plus X? You have to think about what the reaction is capable of doing as it goes to equilibrium. Initially, I have nothing on the right side. I am unable to have my products react. And so I can only move towards making products. Well, eventually this will reach equilibrium. I'll have 0.10 minus X. I will have, well, just X. And I will have X for my products. Well, with a Ka of 10 to the minus 7, the top is going to be very small. X is probably not going to be very large. So it's reasonable to say that our starting material is pretty close to its original value. We're not going to subtract very much from it. Well, let's solve for X then. 4.5 times 10 to the minus 7. So remember, we're setting up our Ka is equal to our products, which is H plus and base, HCO3 minus, all over our acid, H2CO3. And so our Ka, 4.5 times 10 minus 7, that's going to equal X for our H plus, X for our bicarbonate, all of that over 0.10. This will give us 4.3 5 times 10 to the negative 8 equals x squared. X is going to equal 2.12 times 10 to the minus 4. So we take the square root of both sides to solve for x. So we have x. We said x was the amount of H plus, and we're in 1 liter. So it's that amount divided by 1 for molarity, which means my concentration of H plus is equal to 2.12 times 10 to the minus 4 molar. My pH will equal the negative log of my H plus. So my pH is going to equal 3.67. So carbonic acid is, on its own, pretty darn acidic. It's an acid. It's going to be reasonably acidic. And so it's not as low as the acetic acid was in video 3, but it's lower than the ammonium was because it's more acidic than ammonium. We saw that from the Ka values. Acetic acid Ka was 1.8 times 10 to the minus 5. Our H2CO3 is 4.5 times 10 to the minus 7. And our ammonium was 5.6 times 10 to the minus 10. And so the bigger the Ka, the more acidic, because the more we'll have on top, which is our H plus and our base. And so we'll leave more H plus around if we have a higher Ka. So we were able to solve for that proton coming off of H2CO3. But there's a funny thing about this molecule. HCO3 minus can either be a base and pick up a proton, but it can also give away a proton. There's a name for it. It's amphoteric. Fancy name that just means it can both be a base or an acid. In our original reaction, when it was H2CO3 breaking apart, our bicarbonate was the base. But bicarbonate can give up a proton, and so it can also be the acid. So there's some space. Well, this actually has its own Ka. In fact, it's called Ka2 for the molecule. And for carbonic acid, that is 4.7 times 10 to the minus 11. So comparatively, just scroll back a little bit, we had 4.5 times 10 to the minus 7, so 10 to the negative 7, versus 10 to the negative 11. It is a much smaller Ka, which means this second proton is far less acidic. It doesn't really want to come off, but a little bit can, which technically means there's still a little bit of extra H plus that will show up. And so how does the fact that there's this second step affect our pH? For this, we're going to take our initial as the amount we solved last time. Like we solved the bicarbonate. We said bicarbonate was X. And so we know that X here was 2.12 times 10 to the minus 4. H plus, well, that's still in solution from from carbonic acid. And so it also is 2.12 times 10 to the minus 4. It's just the two products from last time. Our carbonate, our CO3 2 minus, none of that has formed yet. So what we're looking at here is we had our first reaction, H2CO3. Some of it broke apart, gave us HCO3 minus and H plus. And then HCO3 minus breaks into more H plus and CO3 2 minus. Well, any bicarbonate that goes away means that more carbonic acid breaks apart. And so they actually all feed into each other. Full calculation is a little complex. But it does let us start and look at the simplified view, which is whatever amounts of product I made from my first reaction, that's the amount that starts my second reaction. And so that's why the values for X are used for bicarbonate and for H+. There's going to be a change. Well, I don't have any carbonate. So again, if I'm missing one of my products, I cannot do the reverse reaction. There's none of it to react. So my only option is to lose bicarbonate and gain H+ and gain carbonate. I'm going to reach equilibrium. Well, again, Ka is even more tiny than before. Our assumption that X is going to be small, that's still going to be true. So despite a little bicarbonate going away, it's still going to be pretty darn close to 2.12 times 10 to the minus 4. Despite gaining a little H+, well, this time is a little different. We've never seen this before. But that X is going to be so small, it's still going to roughly be 2.12 times 10 to the minus 4. However, carbonate will definitely be X. So we can plug this in. 4.7 times 10 to the minus 11. It's going to equal 2.12 times 10 to the minus 4. It's going to equal X. So our products over our acid, our bicarbonate, 2.12 times 10 to the minus 4. Those basically cancel. Because they came in on both sides of the equation equal, and the Ka is so small, I mean, even if we change them a little, they largely cancel. They both put the same amount on top and bottom, which means X for our carbonate is really going to be basically the Ka2. It's going to be 4.7 times 10 to the minus 11. And indeed, that is incredibly tiny. If we subtracted that from the acid, it wouldn't meaningfully change the number. If we added that to the H+, it wouldn't meaningfully change the number. Now, technically, we did break a little part of our bicarbonate apart and make a little bit of acid, but so little came apart that for all intents and purposes our acid is still the same starting amount. Our H+, sorry, H+ is the same starting amount. Short version of the bullet points then at the end. Technically, a diprotic acid, a weak diprotic acid, we're not talking about the strong ones. A weak diprotic acid does give away multiple protons. However, as you can see by the amounts, 2.12 times 10 to the minus 4 versus 4.7 times 10 to the minus 11. The extra in the second step versus the first step, there's basically none. The second step does not meaningfully increase the H+. What this means is that your pH is based on first step. Your pH will be based on the first step. The acid from the H+ from the second step won't change the concentration enough to alter the pH. Not if you already have the first step. And so it's just a neat thing when you have diprotic acids. They do indeed go through a second reaction. They just don't do it very much, especially compared to the first reaction. It's a lot harder to give away a second proton, well, because it's positive. Positive things are attracted to negative things. far more than they're attracted to neutral things. And so having a H2CO3 lose 1, well, then H plus left a neutral molecule. But having bicarbonate lose 1, and H plus leaves a negative molecule. That's just harder to do. And so as a result, it's got a smaller Ka, and less of it succeeds at breaking apart. All right, there is a look at a diprotic weak base and how they can be a little funny. In terms of calculations on exams, might ask you to do the first step, but you would not be asked to assemble both steps. Just wanted to highlight what's going on when you indeed have a weak acid with more than one.